Good. Excellent. So, you guys are the first guys I've ever sat in the front row. Usually everybody sits up in the back row. Thank you. It means a lot to me. We're going to talk today about, we've talked, over the last 3 weeks, we've talked about specifically about what the projects we're doing here. We talked a little bit about what we do as a company in order to determine what type of project we're going to do, and the important ways that buildings use energy and how energy is produced. And so today, what I'm going to do is take it through some information on 2 different ways that we assess whether a particular project can be done. And the first thing I brought for you to look at is this is a small solar panel. It's pretty much just this aluminum frame around an acrylic piece on the front and a plastic piece on the back, and then sandwiched in between is a razor thin piece of silicone kind of painted onto it. You can see the electric wires. Those lines are the electric wires. Electricity gets picked up by those wires and then outputted in just a little red and black cable. These get plugged into the inverter, and then voila, you have power. Now this panel is, we use this panel for a remote device to measure wind data. So I told you that you can't really do a wind project unless you know what the quality of the wind is. And this is the unit that actually measures that. It's called a anemometer, because I can't say the word. I always put too many N's in it. This is Mike. Mike is one of my partners in Revolution Energy. And good job on taking your hat off. In the bottom here, you see that there's a little Cat 5 cable plug. And so a cable just goes into the bottom of that. And then when the device is spinning, the data gets recorded and output into a recording box. So I have some pictures of that.
I had a quick question too on the solar panel. You had said that it gets converted, so it comes out as DC, power, and then
Yes.
Okay.
And the panels we'll be putting on are much bigger than that?
Much bigger. Yep. Yes, 3.5 by 5 feet, and 400 of them. So this is Mike. Mike, you wearing the same thing you were yesterday?
Different story.
All right. This is the anemometer at the top of the pole. See it way up here at the top.
That's what you were doing. You were trying to figure out how do I jump up there and get it.
Yeah, well, the pole actually, it's a telescopic pole. So each section you just individually. So this was actually when we were taking it down, and this section down here was getting stuck. So this is one section right here. So I had to try. I'm like, well, how is this going to work? Because it froze, and it actually bent. So the wind had bent the whole thing before we put the guy wires on. And so I had to reach up and try and keep pulling down the higher portion of it on that nice sloped angle. So that was fun.
Extension ladder? Just need an extension ladder against it?
It would have helped. I didn't. No, actually, that wouldn't have helped in that situation. But I just.
So we're on top of a building. The pole is bolted into the walls, and then the pole is 35 feet. So the anemometer was about 15 feet in the air, which is probably where a good location for a residential size wind turbine for this site. And this is 1 day of data. And you can see every single minute we get a point, and that point tells us what the wind speed is. So you can see the wind speeds going up and down and up and down. At night it was low, and then it started coming up during the day. You know, a residential turbine may start spinning around 7 or 8 miles an hour, and then it'll keep going at about 6. So as long as it gets a startup, it can keep going at a lower speed. So this probably would have been a decent day for wind on that day. Some of the new turbines that are coming out, they're trying to get a lower startup speed, because obviously if it starts up lower, it'll produce electricity more. And we're going to get the software necessary to crunch all this data, and it'll tell us, based on where the points are, how often the turbine would have run, how often it would have started up, and then how much electricity would have been output. I'm going to go through a little quickly because I want to get the welding students over to the boiler room because they're welding today. The pole originally bent, so we had to put up these guy wires. Now, if we can find any space, if we wanted to put up the anemometer here on, I hate that word, on this campus, we can try and find a space where we can put it up and then guy it up, and maybe even on the roof, and we can take a year's worth of data. We did about 14 months worth of data. This is how it's clamped into the side of the building. So just 2 points, drilled holes, and lagged in the bolts.
So you were saying that it may run at a constant 6 miles an hour or 5, but it needs a good 7 or 8 to actually get it to initially spin.
Right. It's like you know, the getting an object from into motion requires more energy than it does once it's to keep it into motion. You know, that initial push to get a car moving takes so much more force than the amount of force it takes to keep it moving.
And the more wind, the higher output. So, it's able to run at a lower speed after that initial startup speed. That's the difference. So if you do have more wind, it is beneficial.
So the wire comes out of the bottom. Out of this, we used a really thick rubber hose to protect it, and then it goes into a yellow box, and then the solar panel is connected to the box, and that keeps the battery running in the box. So you can put this thing up anywhere. You don't need a power supply to run to it. The last device that we use is a thermal imaging camera. And now we're switching gears to building science a little bit. And this is what it looks like. And this little thing costs $5,000. They're really expensive. And this is the kind of image that you get. I'll show you some better images. But the goal of this device is to tell you where or heat is leaking out of a building. This is what we use it for. Because when you put heat into a building, you want it to stay in. The more heat that leaks, that's what costs you money. The other way we use it is also to see, you can use it to kind of tell where power is being used. In some cases, you can see where bad wiring is located. But we primarily use it for heat source.